Welcome to the video lecture on speed control methods for DC motors. Before the close of the university, we were looking at the fundamentals of DC machines. Then we looked at different type of DC motors, what are their equivalent circuits and torque speeds characteristic curve. So we will continue the sections that we covered, and what we need to cover next is the speed control methods for DC motors. I have uploaded the gapped handout related to speed control of DC motors section in the e-learning system. So you may download the presentations and you may fill the gaps in the handout. First, we will look at why we need the speed control techniques. As you see the torque speed characteristics, depending on the torque that you would get, you will be operating at a different speed. When you consider practical operations of a machine, you may be need to operate at a certain torque level or else in a certain speeds. So to make sure that you are operating at a certain speed or torque, you need to control the speed of the motor. By doing that, you may be increasing the efficiency, or you may meet the application specifications, or else you may be negating the disturbance acting on the motor. So you can apply different speed control methods for different DC machines. In this section, we will look at what would be the possible speed control techniques for shunt DC motors and series DC motors. First, we will look at the shunt DC motor. If you recall your knowledge that you gain for the shunt DC motor, the torque speed characteristic equation for the shunt DC motor is given by this equation. Omega is equals to minus RA over K phi squared times tau induced, torque induced, plus Vt over K phi. So it relates the speed and the induced torque. So if we look at this equation, we have parameters in this component and we have parameters in this component. So we could see that we could change the torque speed characteristic equation if we can change the RA value, that is the armature resistance. Then you could control the flux inside the machine. Thereby also you can change the characteristic equation. K is a constant for the machine, so you cannot change that parameter. Then if we take this component again, if you control the terminal voltage, you can control the torque speed characteristic equation and you can change the flux. So based on that, there are three methods available for speed control. First one is the adjusting the field resistance, that is the change in the flux inside the machine, adjusting the terminal voltage apply, inserting a resistor in series with the armature. So basically these last two methods are relating the armature current control method. So indirectly you are controlling the armature current. So by inserting a resistor in series with the armature, you will be changing the RA value. Adjusting the terminal voltage apply is VT control. So we will look at one by one. So the first one is the vary the field resistance. So this should be corrected. It's not the vary the file resistance. This should be changed to field resistance. So if we look at the field equation, IF is equals to V terminal over RF plus R adjust. So here RF is the field winding resistance and this R adjust is the external variable resistance. So by controlling R adjust, you can control the amount of flux generated inside you could control the field current, thereby you can control the flux inside the machine. So when you control the flux inside the machine, that will change the internal generated voltage because phi is changed. So when you change EA, you could control the torque. So you could see the armature current is equals to terminal voltage minus induced internally generated voltage over RA. So what you could see here is that if you change the flux, you are changing EA. That means you are changing the torque generated current flowing to the armature. Then the induced torque is equals to K phi IA. Therefore, you can control uh, the induced torque. So this characteristic curve relates the speed of the motor against the induced torque. So if you have two field resistance values, then this would be your characteristic curve. So when you change the when you have a higher field current, your characteristic curve would be in this manner, and if you have a lower field current, then your torque speed characteristic would be in this manner. So if you go back to the torque speed characteristic curve, so when you change the field current, you will change the gradient as well as the intersection point. So when you have low flux, your intersection point would be higher, and when you have higher field current, it is going to be intersecting at a lower value. And in the similarly gradient, if you have a higher field current, then gradient would be less, and if you have lower field current, gradient would be high. So that you can relate here. So RF1 has in having the higher field resistance, so you have a lower intersection point and lower gradient. RF2 is having a low field current field resistance, so you have a higher intersection point and higher gradient. So I assume that you are clear on that. Then we will see what is actually happening when you change the field resistance. So it is not if you recall this equation, look at this equation. When you change the field current, EA is going to change, so you have your IA is going to change. At the same time, if you look at the induced torque equation, it is K phi A. So when the field resistance is changed, flux is going to change as well as IA. So if you increase the field resistance, flux is going to reduce. So if flux is reduced, then internally generated voltage is going to reduce. That means actually IA is going to increase. So you would see a decrease in flux and increase in the armature current. So we will see what is really going to happen. So if you increase RF, that is going to decrease the IF value. If you increase the field resistance, that is going to reduce the field current. If you reduce the field current, that is going to reduce the flux. Once the flux is reduced, it is going to lower the internally generated voltage. So when internally generated voltage is reduced, it is going to increase the armature current. So when the armature current is increased, the torque is going to increase in the machine. When the torque is increased, that is going to increase the speed of the motor. Once the speed is increased, EA is going to increase. So when the EA is increased, IA is going to decrease. So IA would decrease until the induced torque and the log torque are going to be equal. So you can look at these steps leisurely and see whether you can understand the cause and effect when you change the field resistance. Second method is inserting a variable resistor to the armature circuit. So normally this is the armature circuit. So now you have a external resistor connected in between the armature winding and the supply. So your field circuit is not interrupted, you are only interrupting the armature circuit. So when you add an external resistance, what you are basically changing is the effective armature resistance in the circuit. So now your armature current would be Vt minus Ea over Ra plus R external. So now when you change R external, you can change the Ia value, thereby you can control the torque uh, generated by the machine. One thing you have to remember is that when you insert a resistor here, you are not affecting the field circuit, therefore the flux inside the machine is going to be constant. So when you take the induced torque is equals to K phi Ia, so phi is constant, therefore torque is directly proportional to the Ia value. So when you change the field resistance, what you basically changing is the gradient of the torque speed characteristic curve. So if you refer back to the torque speed characteristic curve, the intersection point won't affect from the Ra change, it is going to change the gradient. So if you increase Ra, gradient is going to increase. If you decrease Ra, gradient is going to decrease. So that you could see here in the characteristic curve. So Ra is higher here. So when you have Ra1 is lower in this one, so you have a lower gradient. Ra4 is the highest resistance, so you have a higher gradient. So but the disadvantage of this method is that you are going to add an external resistance. So when current is flowing through the path, it is going to dissipate energy. So that's the main disadvantage of this method. Third method is change in the armature voltage. So basically this is the armature circuit. So you are going to change the voltage applied to the armature circuit. So you get the supply from the whatever the source that you have, and that is fed into the field winding, and in between this point and here you have a variable voltage controller. So that means that is an additional electronic circuit which is going to change the effective voltage applied to the armature circuit. So now the you are you will in this method you are not changing the flux inside the machine. So Ea is going to be constant. So what you are changing is the Vt value that you are going to apply to the machine. So Ra is going to be constant. So when you consider the torque speed characteristic equation, flux is constant and Ia is going to vary depending on the applied voltage to the armature circuit. So in this method, when you change the terminal voltage, it is not going to vary the gradient of the torque speed characteristic. So if we go back to the torque speed characteristic equation, so you could see here Ra is going to be constant, flux is constant, therefore the gradient is constant. Only place where the torque speed characteristic equation is going to change is the intersection point. So when the voltage is high, intersection point would be high, and when the voltage is low, intersection point is going to be low. So that is what is presented here in the torque speed characteristic. So Va 2 is the higher voltage, so So you have a lower uh, intersection point. VA1 is VA1 is the lower voltage. So actually these 2 points should be curves should be interchanged. When you have a higher voltage, the intersection point should be high, so this should be VA1, and VA2 should be VA. This should, sorry, if I repeat again, VA2 is the higher voltage, so you should have a higher intersection point. Therefore this curve should represent VA2, and VA1 should be represented by this curve. So you could see we discussed three methods for speed control of the shunt DC motor. First one is changing the field resistance. Second one is changing the armature resistance, and finally we discussed the varying the armature voltage. Now we will look at speed control of a series DC motor. So when we look at the equation, omega is equals to Vt over square root Kc times 1 over square root tau induced minus Ra plus Rs over Kc. So basically what we do in this method is that we will use resistor in series with the supply to control the speed. But when you insert a resistor, that is going to generate heat, increase the heat dissipation, which is going to reduce the efficiency of the machine. Now we will look at the DC motor selection and applications. So when you are selecting DC motor, you have to look at the size of the motor, what type of load that you are going to connect, duty cycle. What is meant by duty cycle is how often you are going to operate the motor. So if you have a higher duty cycle, then it is going to wear and tear quickly, and if it is not working regularly, then it is going to reduce the wear and tear. Then you need to look at the operating voltages and the environment which you are going to use the DC motor. So DC motors are used in different applications. So you could find fans, hard drives which are working in computers. In vehicles, you have the starter motors, wiper motor, power window operating motor. So there are a lot of ones. Then other than that, there are DC motors operating used in lifts, rails, fans, blowers, centrifugal pumps, lathe machines, etc. So with that, I will conclude the section on speed control techniques for DC machines and DC machine selection and application section. So these are the references that I have used